Okay, welcome back. We're going to talk about logic games today. Specifically, we're going to talk about linear games. Linear games are probably one of the more common game types on the test. The example that you see in your book with the comics scheduled to perform in a comedy competition is a very good illustration of the basic category. You see in that scenario that each of 7 comics, J, K, L, M, N, and P, are scheduled to perform in a comedy competition, one act at a time, and each performer performs just once. It's important to note that in this case, there are no ties. Nobody performs at the same time. Any kind of dueling comics on stage doesn't happen. And also that none of the comics goes more than once. They got one shot and that's it. This creates what we call a balanced setup, where the number of available positions and the number of available variables matches up. And that's kind of the ideal setup. It's the easiest kind of a linear game. J, K, L, M, N, O, P, 7 comics, and then each of them gets assigned a unique position. 1, 2, 3, 4, 5, 6, 7 positions. This results in a 1-to-1 relationship, 1 comic, 1 performance, 1 comic, 1 performance. There are other variations possible in linear games. There are 2 other ways that this could happen. Instead of having 7 variables for 7 positions, you could also have more variables than positions, or more positions than variables, number of positions, number of variables. When you have more variables than positions, what typically occurs in a linear game is that somebody has to share. There are some positions that are occupied by more than one variable. Some classic examples of this kind of game might be roommates in an apartment building, or maybe the offices in a office building. And in both of those cases, you'll have a combination of maybe 2 variables per spot, or maybe even as many as 3 variables per spot, and then some other positions with just 1 variable. Okay, so this is considered to be overfunded or overloaded. And then in this case, where you have fewer variables than positions, what has to happen generally is that you have to have repeats. Some variables will appear more than 1 time. Okay, so here, ties and repeats are both not allowed. Nobody goes more than once, and nobody goes at the same time as anyone else. In this case, you tend to have some ties. That is more than 1 element occupying the same position at the same time. And in this case, you tend to have a number of repeats, some variables appearing more than once. The scenario, the paragraph at the beginning, will always tell you what you're looking for. If it's going to be the kind of game where you have to repeat elements, where you have to use elements more than once, or where everybody gets their own spot and it's completely balanced. So pay careful attention to that as you go through the questions, and make sure that you have a sense of that before you even get to the rules. This is something that you should know very early in the game in terms of the overall structure. Okay, so let's go ahead and move from the general discussion here and talk a little bit more about orientation. In terms of orientation, you have 2 choices. Generally, you can set things up horizontally or vertically. I tend to default to horizontal, although I will choose a vertical setup in the cases of looking at buildings, arrangements within a building, or also seating within a plane, a bus, a boat, or something like that. And I think for me, the rationale there for the seating aspect, buildings make sense, they're vertical. For seating, I think I imagine sitting in a seat and looking forward and seeing the backs of the seats in front of me. And I get a better sense of who's in columns versus rows if I can imagine looking down the row that I'm seated in. So for that reason, I'll use vertical setups there. To be honest, it's not that important which one you choose, because all of the games can be done either vertically or horizontally. The main difference is how you then draw your rules. Make sure that the rules are calibrated to your main setup. All right, with that, let's go ahead and turn and look at the rules. So turn the page and look at the linear rule representations. Okay, so as you can see here, I've drawn both a horizontal and a vertical setup. I'm going to try to walk you through how the rules should be diagrammed in both cases so that you're prepared for either kind of setup. The first and probably most common type of rule that you'll encounter in a linear game is what's called a not law. And that simply specifies that a variable cannot occupy a certain position The book, for example, talks about J cannot perform first. Out of my comics, J cannot perform first. It's up to you what you choose to be first here. I'm going to use the top as first. And in that case, I'll just put a little bit of room underneath the first and second spaces, second and third, and so on. Fill that one out, all 7 spaces. Make sure I have a little bit of room so that I can put these not laws in. Another way to do this is to use left and right. And in fact, that may work better here. To say that to the right of the diagram, I'll list the things that can't appear in a certain spot. Horizontally, pretty straightforward, just use beneath. Okay, so those are basic not laws. Most common inference, it's useful, but it typically doesn't link to other ideas. And as you become more accustomed to these types of games, you may find that you don't use not laws quite as often as you did right at first. Okay, the next rule type that we're going to talk about is block rules. Block rules have to do with adjacency. So you might be told that O and P perform with P performing immediately after O. They are locked together in this order. And this is for the horizontal diagram. You can see that this block can only appear in 6 different positions, 1, 2, 2, 3, etc. If I wanted to represent the same rule for my vertical diagram, I'd have to orient it differently with O at the top and P at the bottom. And again, then same range of positions, 1, 2, 2, 3, etc. These are pretty useful because they involve both 2 variables and 2 positions and limit the number of possibilities dramatically. So we like to see block laws. Block laws can become even more powerful when you expand the number of variables involved or the number of spaces involved. An easy way for the test makers to add more spaces to this is to say that O's performance precedes P's performance with exactly 1 performance in between. I won't redraw it over here, but basically just orient it on its side again to get the vertical setup. And here I have O space P. So now I'm accounting for 3 spaces and 2 variables. And of course, the number of places this can appear in my main diagram is now even fewer. We've got 1, 2, 3, 2, 3, 4, 3, 4, 5, etc. When I know that the order is fixed in a certain way, that O precedes P, this is more powerful. It can become less powerful if I'm told that they are adjacent to each other, but the order is unknown. And when I'm not sure what the order is, I just make a minor modification to the diagram. I don't want to change it dramatically. But I enclose the entire group in a circle or an oval, if you will, instead of a square. The oval to me suggesting that the order can be different. It could go O space P or P space O. The less certainty you have, the less powerful the rule becomes, and the more that you still have to solve in each case. There are lots of different directions test makers can go with these. Another possible approach is to say that O and P aren't together after all. They're not together in that specific order. So perhaps P can come right before O, but it can't be O then P. Or they could say O and P just do not perform back to back, in which case you've got a not circle. So we have block rules, expanded block rules, circle rules, not blocks, and not circles. And each of those means something slightly different. I'm going to focus just briefly on the implications of this one, and then I'll let you think about the implications of the others. If O and P are together in that order, and I know that O always precedes P, that also tells me that P can't perform first, there'd be no room for O, and that O can't perform last, there'd be no room for P. So these rules are powerful in the sense that they tell me both what's going on, as well as giving me some not laws to work with. Okay, at this point, your book has kind of a brief aside about the difference between blocks and sequencing. When you think about a block rule, that tells you the position of both variables. If I know where P is, I know where O is. If I know where O is, I know where P is. A sequence simply gives you a relative position. So when O is fixed, P still has a number of options depending on where O is. This can play out in 2 dozen different ways. This can happen just 6 ways. But the not laws are the same. In both cases, I can say that P can't be first and O can't be last. The longer the chain becomes, either a sequencing chain or a block, the more I know. And in both cases, the inferences are the same. if L is before O is before P, or L precedes O precedes P, whether they're adjacent or not, then I can say not only is P unable to be first, but O can't be first either. It has to be after L. And P can't be second either. On the back end, L can't be second to last or last. So I go from 2 not laws previously now, and now I've got 6. Your book goes through a couple more examples like this, but there is an overlap between sequencing rules and linear rules. However, linear rules can be more powerful than sequencing and can actually reduce the number of options even further than sequencing rules can. Okay, with that, let's talk about 2 more types of rules here. We also have what are called split options and dual options, which I'll cover momentarily. Okay, you see here what we have, an example of what's called a dual option. That is where there are 2 elements for a possible position. In this case, L or J performs third. One of the mistakes that students sometimes make on linear games is to focus exclusively on what we know about the variables. But if you only think about the variables, you sometimes miss out on valuable insight about the positions. In this case, our focus is on position 3. When this will matter the most is when I'm actually able to determine something about L or J. So for example, if a question says, if L is 2, ... If I know that L is 2, what does that tell me? It's obviously a pretty straightforward example, an easy one. But if L is 2, then it's no longer an option for spot 3. Therefore, J must be 3. Once L is taken out of this spot, J is the only remaining option to fill that spot. These split options are pretty useful, especially in terms of inferences on local questions. Another type of question that you might see, type of rule, might be that the same variable is limited to one of 2 positions. Okay, I'd like to note here that in both cases I've drawn one of the L's on the left-hand side and one on the right-hand side. This is deliberate. I like to keep the scenarios separate from each other so that I could fill this in and say, maybe this is JKLMNOP or JKMNLOP. And my left-hand diagram and right-hand diagram would form 2 complete diagrams that are consistent internally with no overlap. So wherever I can with these splits, I'll try to put one of them on the left and one on the right. It's not always feasible, but usually you can do that. What this becomes useful for then is if I can say something else fills one of these 2 spots. Let's say if J is 3, comma. All right, what can I infer from knowing that J is 3? And if you look at your diagram, think about the rule, the implication of J3 is, of course, L not 3, therefore L 5. So these split and dual options are both pretty useful, and you'll see examples of each of them in your games. I believe the first game that we're going to do in class actually has one rule from every category. A not block, a block rule, a sequencing rule, a split rule, and a dual rule. So we'll see all of those when we get together in class. But for now, these are the rules we've covered. So thanks a lot.